Hey everyone, welcome back to Ask Becca About Space. Today I am still up north on the island. I will be here for the next few weeks or so, and everything is still fine. I'm very happy to be up here, and in Oslo, things are returning to somewhat usual. Our university has, or at least our department is open to 50% capacity. So everyone who that 50% is able to accommodate everybody who wants to come in to the office. Most people are still in home office because there are some concerns about public transport opening back up. It's been open, but people actually using it is another story. And people going back to work will probably see more of a surge of public transport use. So a lot of people still prefer to work from home, and I prefer to work from the Arctic. So that's where I am. So today is kind of a cool episode because it's Ascension Day today. So in Norway we have that day off. So I've started the day watching some Doctor Who episodes so that I can prepare for Lillian's questions, which is super fun. But the first thing that Lillian wants to know is just some of my favorite facts about the sun, which is great because that's my job, to think about the sun. And honestly, my favorite facts about the sun have changed a bunch in the past several months because specializing in solar physics is something that I didn't do until September of last year when I started this job. I've always liked kind of the sun's connection with the earth in terms of space weather, and we'll talk about that a little bit more later. But kind of recently, my favorite facts about the sun have been things that I've just learned about the sun, and in particular, things about the sun's magnetic field where the sun is not particularly active. We've seen over the past week or so that it I mean, I can't blame people for not knowing that the sun has, weak magnetic fields all over its face, because we've only just been able to detect those weak magnetic fields, right? And that is what I study. Some of the things that we've been learning lately about those weak magnetic fields that exist all over the sun's face, not just where the sun is obviously magnetically active, the entire sun is magnetically active. So some of those things that we've been trying to kind of nail down over the past, well, me for the past couple of months, but the community for the past couple of decades or so, is how are those weak magnetic fields distributed across the sun's face? And we're finding, kind of surprisingly, that instead of having kind of magnetic flux tubes that face us all the time, the majority of those weaker fields are actually horizontal fields that are kind of perpendicular to the sun, or I'm sorry, parallel to the sun's surface rather than perpendicular to the sun's surface. The sun's face is organized in what we call a granular structure, or the network and the internetwork. And what that means is basically we can see these kind of granules or parcels of plasma individually as they experience kind of convective motion. And we have upflows and downflows of plasma in the intergranule lanes, or the boundaries of those parcels of plasma. That's usually where, of course, we see those vertical magnetic fields, or the ones that are perpendicular to the sun's face, in those boundaries. But in the internetwork, on the face of those granules themselves, we're seeing a lot of parallel fields that are weak and relatively difficult to detect. But the fact that we can see them in observations and computer simulations tells us that maybe there are some kind of local magnetic field generation processes which generate that field, but maybe those processes aren't enough to see the distribution in both field strength and angle of the field, whether they're parallel or perpendicular or somewhere in between, with respect to the sun's face. So that's my favorite thing right now. I'm just kind of learning more about that. I have been looking at several satellite observations from a satellite called Hinode, And I have also been looking at a bunch of different computer simulations from our in-house solar model called Bifrost. So between simulation outputs and the parameters that help shape those simulations in comparison with the observations that we have, I'm kind of looking forward to crafting the narrative of how we can more accurately simulate these weaker fields, and kind of more importantly, how we can better understand these weaker fields on the sun's face. So that's kind of what I'm focused on right now. Now, Lillian, you sent me, or your mom sent me, a little bit of information about a Doctor Who episode, which is actually 2 episodes. This is series 6, episodes 5 and 6, where there is a big solar storm that kind of causes these almost humans, or these flesh humans, to kind of reanimate and start to get stronger. So I guess to just kind of discuss the science fiction and the science reality behind this episode, the solar storm that happens in the episode is a really, really big one. And basically, in the really beautiful kind of graphics of the episode, you can see all of this craziness in the sky, and there's like lightning and like streams of plasma coming down from the sky and stuff like that. And of course, as we know, the way that we experience space weather, the way that we experience geomagnetic storms like that, is in a different layer of our atmosphere. So in the episode, the storm is more or less in the lower kind of troposphere, which is the lower layer of our atmosphere, where we see instabilities that form things like thunderstorms and rainstorms and hailstorms and things that we kind of colloquially think of as storms. But solar storms, or what we call geomagnetic storms, they happen in a layer of the atmosphere that's higher than that. It's called the ionosphere, and it's towards kind of the upper layers of the atmosphere. It's not quite exosphere, but it's a little bit higher than the mesosphere. So it's kind of in the upper middle, or lower higher, I guess, depending on how you want to think about it, layer in the atmosphere. And that's where we see northern lights and southern lights happening as a result of solar storms. The magnetic impulses that the doctor talks about in the episode that he can be able to detect, I mean, it's yes and no. The storm strength has a lot to do with how we receive that storm here on Earth. Most of the time, the storm is relatively confined to, or the brunt of the storm is relatively confined to the ionosphere, where we see most of that activity. But yeah, we are getting an increase in high energy particles like gamma rays and things like that. In an average storm, though, we're not going to feel a whole lot of the brunt of that storm here on Earth. What's affected by these storms is satellites and satellite communications, first and foremost. And that's one of the most vulnerable pieces of equipment that we have that can be affected by the solar storms. Now, in the episode, they struggle a lot with, they're on an island, and they struggle a lot with communicating with the mainland, because during the solar storm, their communication signals are scrambled. And yeah, that's pretty accurate. This is one of the reasons why, if nobody else, the US military will continue to fund space weather research and solar physics research, because the ability to predict how and in what ways our communication satellites could be scrambled or damaged during a solar storm is really important. And the fact is, I think people think that we're better at doing that than we are. Right now, our models are pretty good. Right now, we can see eruptions from the sun that are earthbound about 8 minutes after they happen. And we know we have a couple of days, maybe a day or two, to prepare for what may be a tremendous impact. What we're not good at doing yet is predicting exactly when those eruptions will happen. And then on the other side, exactly how those eruptions may or may not couple to our own Earth's magnetic field, because our magnetic field is what's sheltering us from the brunt of that radiation, because it's a magnetically driven explosion. And so it has magnetic properties. That plasma has magnetic properties that propagate then through space between the sun and the earth. And they are conserved theoretically, but they change. They can change on the way here, right? As plasma travels between the sun and the earth, depending on the dynamics, the speed, the velocity, the energy available, the charge, and the magnetic helicity or the magnetic twist of those particles, plasma shock waves very often form, where plasma gets a little bit condensed against each other, and then heat transfer and energy transfer happens, and this kind of propagates through space. It's difficult to say exactly what we're going to get by the time those that plasma sheet ends up at Earth, or those bow shocks end up at Earth. It's also difficult because once it arrives, because this is a magnetically energetic event, we're not always sure exactly how that magnetically energetic plasma sheet will couple with our magnetic field. Sometimes it doesn't, because it doesn't quite fit, but sometimes it does. And we're just now kind of understanding the fact that magnetic orientation or magnetic twist or magnetic helicity is one of the properties that can determine whether or not we're going to get a good solar storm. So the predictability, I mean, of course, it's the doctor, so he's a little bit of a ethereal being, but the predictability of the storms from the doctor, that's a little bit out of our reach right now. He's able to say these things with pretty much certainty, but we're not able to say these things with pretty much certainty right now. Also, they don't necessarily come in pairs. They don't necessarily come in patterns. We haven't nailed down any sort of local small scale periodicity. The periodicity of the strength of the storms follows the periodicity of the sun's 11-year magnetic cycle, more or less. But other than that, the predictability of the magnetic eruptions itself isn't really nailed down yet. So while a lot of the ideas behind the solar storm in the episode are pretty on par with what the sun does, the storm in the episode doesn't happen at the same level of the atmosphere as the storms do in reality. And we're not able to predict them as well as the doctor is able to predict them. And but these solar storms can have a tremendous effect on our electrical signals. And if the storm is strong enough, they can have an effect on electrical things down on Earth as well. I talked a little bit about the Carrington event in a previous video, and that event, thank goodness, happened in 1859, where we didn't really have the energy grid that we have now. But it did tremendously impact the telegraph network. There were telegraphs kind of just sending and receiving by themselves, which was absolutely wild. But that was a huge storm from a massive eruption that coupled very well with our magnetic field. So it was this kind of once in several lifetimes, probabilistically, event that happened. But statistically, it'll happen again. So it's just kind of a matter of time and a matter of how good we are at predicting these things. And we are getting better. A lot of people are using machine learning and computer simulation techniques to get better at space weather forecasting. It's a very, very active field. And people like me are kind of on the other end of that, on the sun side, not necessarily concerned with space weather forecasting in particular at this moment, but I'm trying to understand how the quieter magnetic fields also drive energy into the atmosphere, because they're not enough to drive those magnetic explosions, but there's too much energy in the atmosphere to be accounted for at the moment by the thermal and magnetic sources that we understand, okay? So my job is to kind of understand how the quieter magnetic fields also contribute to that energy budget in the atmosphere. Okay, so all in all, I really liked those episodes. They were super cool. And I love that the science fiction edge of Doctor Who also pretty well aligns with science reality, even if it is like science fantasy. there are still some pretty scientifically sound concepts behind what was going on in the episode. Okay, so thanks for sending in those questions, Lillian. I appreciate them as always, and I hope you're doing well. I have Lisa coming up, and I think one or two other things on the docket. So I'm always happy to hear from you. I hope you're doing well in the US. Unfortunately, I don't think I'll be able to make it over there anytime soon the way things are. So I am just kind of enjoying my current country of residence for now. But hopefully I'll be able to see some of you guys by Christmas. I don't know. Fingers crossed. All right. Have a good one. I'll see you guys later. Bye. Bless my soul, Herc was on a roll, pushing out the weekend every Greek opinion poll. What a pro! Our Herc had cash to burn. Now new Mauritian famous, he can tell you with a Christian heart. Hercules, Hercules, who put the gliding gladiator. Hercules. Okay, here we go.